Alright, hello everybody. So we're into lesson 7.6, solving problems involving exponential growth. So really this is just like the application aspect of everything we've been learning, alright? So we're taking the exponential functions that we have learned and now putting them towards word problems, alright? Application. Just as we've done in all the other units, I teach you the quadratics, and then we start getting into like projectile motion, or when we were doing trig problems, right? Trig functions, you start to then get into this whole windmill. Well, I showed you exponential functions. Now let's look at word problems, okay? So there's two types of word problems when we deal with exponentials. The first one is growth, okay? And growth really is just another way of saying that you have a increasing function, okay? So increasing. And again, the word increasing is when x values increase, right? So if you read like x1, x2, x3, like as you read a graph left to right, so left to right, that's the direction you read, your y values also increase, okay? Again, that's what an increasing function means. So exponential growth is just a exponential function that models an increasing scenario. So today's lesson is rather short, all right? It's just two examples. So in the first example here, in 1978, researchers placed a group of 20 deer on a larger island in the middle of a lake. The deer had no natural predators on the island. Researchers collected population data and created a graphical model. Okay. So complete the table of values. So what we need to do is we need to just look over and read our x values, right? So like this is coming from the x-axis, and then these ones are coming from the y-axis, the number of deers, okay? Because you can see right here, we are modeling years on the x and number of deer on the y. So just simply look at the graph at the x point and read off the y. So if I go to year 0, again, year 0 on the x right here, this right here, okay, so I see a value of, well, if 2 ticks is 40, that means 1 tick is 20. So it looks like every one of these squares going up is a unit of 20. So at year 0, we are at 20. Okay. And I'm going to intentionally put this in a different color, this next point, because I want you to see a pattern when we start answering the questions, okay? So if I look at year 4, well, let's go up. And it looks like we're halfway between 20 and 40, so this would be a value of 30. So let's do 8. So we go up here on 8, read it across. Okay, well, that's at 40. Do it again, right? At 12. So 12, you go up, okay? And then you read across. Oh, sorry, that line looks off. There we go. And read across. And it looks like we're, at 60. 60. Okay, let's keep going. 16, read it across. So 16 go up, and then read across. You're at 80. And then go again. 20, go up, read across. You're at 120. 24, go up, read across. You're at 160. All right, 28, go up, and then read across. You are at 220. So 220. And then 32, oh, looks like we can't go up. Okay, so let's just pause there for a second. All right, so we've almost filled in the table. So we'll get back to it in a second because I know where we're going with that. So let's answer question A. What features of the graph indicate that this set of data might represent an exponential relationship? So this is where I wanted you to, or this is why I intentionally put these into different colors. So an exponential relationship. If you think back to what we were doing in the previous lessons, exponential is when you have, for example, something like 3 to the x. And as you start to put x being, values of 1, 2, 3, dot, 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 right? That ends up being like 3 times 3 times 3, dot, dot, dot. So your number increases. So like if you do this math, this would be 9. Do it again. It ends up being 27 every time you multiply by 3, right? So in essence, you would be saying here that you are tripling, right? Like every single time x goes up by 1 increment, you would triple your whatever you have, okay? There is an exponential relationship. It's not like you're going up 1 unit every single time. It's like, no. The difference here, right, going from 3 to 9, right, the first time you triple, well, that has a difference, that has a delta of 6, right, a difference of 6. But then when you go triple it again, you go to 27, notice how the difference is much greater this time. Here, the difference is, 18. So you can see that there is every time you are tripling, you're not looking at differences anymore. There is a growth aspect. You're tripling or doubling or quadrupling, whatever it is that the rate you're increasing. So if we look at the data we've collected and what would determine whether or not this is an exponential, well, let's compare the colors, okay? So if you notice what I've done in green, okay? So here, the first one, my first set of green I did. Well, how many years passed? I started at 0 years and went to 8. So 8 years passed, right? So that's not how you spell years. Years. 8 years have passed. Well, my population started at 20, and after 8 years, it went to 40. So how many times greater is that? Well, 40 divided by 20 is 2. So my population doubled, right? Well, let's look at another 8-year span. Well, let's look at this one. 4 years to 12 years. That is also 8 years have gone by. And let's compare these population. So if I compare 30 and 60, well, 60 divided by 30, that also gives me 2. And let's just do one more to see the relationship, okay? Just pick any combo of 8-year spanning. So if I look at this 16 and I go 8 years across, right? 8 years across. Well, does my population double? Well, let's look. If I go here and I say, 160, and I divide that by this 80 right here, yeah, it doubled. So every time I span 8 years, it is looking like my population, not looking like it is doubling. My population is doubling. So if I answer question A, what feature of the graph indicate that the set of data might represent an exponential relationship? Well, when moving across a specific x interval, okay? When I say specific, this could be anything, right? In our case, it was 8 years, right? We spanned 8 years. When moving across a specific x interval, the y values increase at a constant rate, okay? So that's what you're looking for when you're looking for a relationship. So now if we say describe a way that you can use the data from a graph to determine whether or not there's an exponential relationship, well, in our case, every 8 years, the population doubles. All right? So what you're looking for is this every 8 years. This is your specific interval. Okay, this can change, right? It might be every 2 years. It might be every year. This is your specific x interval. or your set X interval. And then this right here is the population doubles. This is the constant, and I said rate. Rate is the wrong word here, sorry, my apologies. Ratio, constant ratio, all right? Because it's y2 divided by y1. That's a ratio, not a rate. Okay? So this is your constant ratio. So use the graph and your table of values to determine when the population will be greater than 320. Okay, so if it's saying use your graph, use the graph, and then it says using your table of values. Okay, so we're going to do this two ways. So if I use my graph, well, I mean, the graph is going to be a very rough estimate. So when it says use a graph, let's kind of extend the graph. Let's extend the graph, trying to keep the same kind of curvature, right? So it might do something like this, kind of going up, right? If I follow that trajectory, that looks pretty good. Yeah, you can kind of see the curvature is the same. Well, if I estimate the graph, well, if I go up here and I read across, it looks like if I just kind of estimate here, all right, at 32 years, the population equals 320. All right, just reading off the graph. All right, so I should have done that in purple, but so from the graph, we estimate the population to be 320 after 32 years. So when will it be greater? Well, eventually we're going to answer that question, okay? So pretty much if the population is 320 after 32 years, so pretty much any time after 32 years, all right? But let's also just compare that to our table of values. Let's look at our table of values. Let's see if we actually got the same answer. So if from our table of values, if we wanted to estimate this answer right here, well, we know that every 8 years it's doubling. So go back 8 years from 32 years. Well, that would be right over here at 24. So if I span 8 years, what I need to do is I need to take this 160, and I need to multiply it by 2. And I would get 320 because I know that every 8 years we double. So after 32 years, the deer is 320. So from the table of values, at 32 years, the population is 320. Okay, but let's put this in context because after 32 years or at 32 years, well, let's look what that's actually modeling. Year 0 is technically years after 1978, okay? So if year 0, so 32 years past, 1978, right? Well, that's going to bring us into 2010, right? So that would be 1978 plus 32. Well, that equals 2010. So therefore, the population will exceed 320, okay, after 2010. Because in 2010, right, in 2010, it is 320. So from the table of values, at 32 years, the population is 320. So if we want to know when it will be greater than it, well, it just needs to be past that time. So that's why it's after 2010. Okay, so let's look at example 2. Example 2. For his science project, Joseph placed agar, a gel made from seaweed, in a petri dish and infected it with bacteria. The measurement of the growth ring was used to estimate the number of bacteria present. Joseph measured the growth ring for 2 weeks. He constructed an exponential growth model using the function n of t equals 5 multiplied by 1.2 to the power of t divided by 2. Okay? If this is hard to read, I can just write it again right here. This is the function n of t is equaling 5 multiplying 1.2 to the power of t divided by 2. Okay? So your exponent is t divided by 2. And then it tells you that n of t represents the bacteria present. Okay? So this right here, this is the number of bacteria. And this right here is the time passed. Time in days, okay? Time passed in days. Number of bacteria, and this one was measured in thousands, it says. So, if you're given a formula and it says calculate the number of bacteria present at the start of the experiment. Okay, so again, at the start. So present at the start. When you're dealing with these word problems, like when you think back to quadratics, when you're modeling something that has to do with time, okay, in our case, time is one of your variables. When you are at the start, that should indicate to you that I'm asking you to substitute t equals 0 into the problem, okay? So in this question, it's saying calculate the number of bacteria, so it's asking you to solve for n of t. That's what the problem's asking. And it is telling you to calculate it when t is 0. So if we have our formula, n of t equals 5 1.2 to the power of t over 2, well, I'm asking you to solve for n of t. So n of t, but you're calculating it at 0. So you're substituting in 0 for t. So that's 5 multiplied by 1.2 to the power of 0 divided by 2. Okay? Because again, just like any function notation, whatever goes in here, right, you're replacing the t with 0. So that means you replace the t up here with 0. Right? You're substituting in the variable. So n evaluated, the number of bacteria evaluated at 0 is equal to, well, how do we do this? Well, the first thing you need to do on your calculator is you need to evaluate the exponent, okay? So we have 5 multiplied by 1.2 to the power of, what is 0 divided by 2? Well, 0 divided by 2 is 0. Okay, the next thing that tells you to do, well, you have to follow the rule of bed mass, right? So the operation that is occurring between this 5 and this 1.2 right here is multiplication. So that's this m right here. So you need to deal with your exponent first. So you need to deal with this 1.2 to the power of 0 first. So you go like this. N of 0 is equal to 5 multiplied. Okay, now what is 1.2 to the power of 0? Well, use your calculator, but also you just know from your exponent laws that anything put to the power of 0 is just going to be 1. So 1.2 put to the power of 0, this simplifies to 1. All right, well, then you have n of 0. N evaluated at time 0 is 5. Right? 5 times 1 is 5. So calculate the number of bacteria present at the start of the experiment. Well, there's not 5 bacteria, because remember, your answer is in thousands. So therefore, at the start, there are 5,000 bacteria, okay? Because this is measured in thousands. All right, so just careful with that. So how many bacteria were present after 1 day? Okay, so again, how many bacteria? Once again, you are asking you to solve for n of t. You're asking for the number of bacteria. And it's asking you to evaluate it after 1 day. So if t is measuring time in days, well, after 1 day, this would be when t is 1. Okay, well, this would be after 2 days. This would be when t is 2. And after 7 days, this would be when t is 7. So let's do this algebra 3 times, okay? So n of t, right, when t is equal to 1, what is the number of population? Well, n evaluated at 1 would be 5 multiplied by 1.2 to the power of 1 over 2. So, just as we've done in previous lessons, make sure you evaluate this first. So you're evaluating 1.2 to the power of 1/2 first. So 5 times, take your calculator. All right, I have to do this because like these are crazy numbers. 1.2 put to the power of 1/2. All right, 1/2 is the same thing as saying 1 divided by 2, or 0.5. So this number evaluates to 1.09. And if you were actually going to write out the decimals and not use your answer button on your calculator to carry this forward, then write out a lot of decimals, okay? So that way your answer, right, is not rounded at all. And then you go 5 times that. But see, I wouldn't necessarily need to write all my answers because I'm just going to use my calculator. I'm going to go 5 times answer. And that's going to be 5.477. I'm going to round to 3 decimal places. And why am I doing that? Because I want to go to the thousandths decimal place. Because what this is telling me is therefore, after 1 day, there are 5,477 bacteria after I multiply this by 1,000. Multiply by 1,000 to get that answer. You're measuring it in thousands. So let's do this math again, but for the second one. So it asks us to evaluate it at 2 days. So just another day has passed. And notice this is an exponential relationship because your variable is in the exponent. We have the variable t in the exponent. This function is in terms of t. T is your exponent. This is an exponential function. Let's see that if you increase your x, okay, so as x's increase, as x values increase, do our y values increase? Because if, going back to the start, if your x increase and your y increase, then you are a growth. You're an exponential growth, okay? So if our answer right here is a number that is bigger than 5,477, we are growing. We are increasing. Let's see. So we are evaluating our function n evaluated at 2. So this would be 5 multiplied by 1.2 to the power of 2 over 2, because we're substituting t for 2. All right, so then this is equal to 5 times, well, 1.2 to the power of 2 over 2 is the same thing as me saying 1 right here. So that's just equal to 5 times 1.2. And 5 times 1.2 is 6. All right, so therefore, and again, it's measured in thousands, so multiply this by 1,000. Therefore, after 2 days, there are 6,000. Oh, sorry, 6,000 bacteria. I should have wrote bacteria here. Okay, so yes, look. Increased. Therefore, growth. It's a growth function. All right, because you increase your x, your y is increased. There you go, growth function. And let's do it one more time for the last one. When time was 7, okay, because it asks you to evaluate at 7 here. So you're taking n and you're evaluating it at 7. So that's 5 times 1.2 to the power of 7 over 2. So that is 5 times 1.2 to the power of 3.5 technically. So then use your calculator. Go 1.2 to the power of 3.5. Times that by 5. Actually, I'm going to undo that by 5. So I get 5 times, so just 1.892929, just to write it out. And then I multiply by 5. Just showing you again, you do the exponent math first. Okay? Then multiply by 5, and you get 9.465. I'm going to go to the thousands decimal place. So therefore, after 7 days, there are, times this by 1,000, 9,465 bacteria. It is exponentially growing, okay? So sketch a graph showing the number of bacteria versus time for the first 2 weeks of the experiment. All right, so you're using your formula, the number of bacteria here. You're evaluating n of t using the same formula for 5, multiplying that by 1.2 to the power of t over 2. So all you are doing is taking these x values and substituting them in for that t right there. Okay? So essentially you were evaluating n evaluated at 0. But we've already done n at 0. We did that right up here. That was the first one we did. So we found that to be 5. Okay? Again, it's measuring it in thousands, so you just put the 5. We also did n at 1. That was in this part B right here. That was this one right here. 5.5, sorry. It was 5.477. So 5.477. We also did n evaluated to. That was 6,000, so that was 6. We didn't do this one, nor this one, but we did 7. We calculated n at 7. That was 9.465. So all we are doing, okay, just to fill in these next columns right here, okay, and what we have done, all we're doing, just filling in these columns, is you're just evaluating n at each of these numbers. So again, you just take 3 in this case, and you substitute it in for that t right there. So this would be 5 times 1.2 to the power of 3 over 2. Use your calculator. All right, so 1.2 to the power of 1.5, because that's what 3 divided by 2 is, times that by 5, and in my case, I get 6.573. Just to be clear, what you are finding, these are x's and y coordinates, right? Like these are ordered pairs. So at 0, you're plotting the coordinate 5. At 1, you're plotting the coordinate 5.477. At the coordinate 2, you're going to be plotting 6. So if we just start putting those first couple in, at 0, you're at 5. You're right here. At 1, you are at 5.477. So that would be like halfway, maybe like right here. At 2, you're at 6, like right there. At 3, you're at 6.5. So again, like kind of like halfway, like right there. And so you just keep doing this math, okay? So just keep getting your ordered pairs. So at n, you're at 6.573. So if I evaluate n at 4, right, once again, you're just taking 5, multiplying by 1.2 to the power of now 4 over 2. So if I do that, that's 1.2 squared. And challenge yourself right now. Pause the video and just do this yourself. And then just press play, forward the video, and see if you get the same answers with me, okay? So times that by 5, just so the video is not being super long. All right, I'm sure you know how to do this now at this point. You are just substituting in a function. So let me get the values for you. 1.2 to the power, oh, I messed up here. 1.2 to the power of 5 divided by 2. Times that by 5. Here I get 7.88. Oh, I should have read that other one up a decimal place, but that's okay. N of 6. So that's 1.2 to the power of 6 divided by 2, times that by 5, 8.64. Actually, you know what? I'm just going to pause the video and I'll just play again from when I have all these filled in. So there's no need to watch me calculate all these. Okay, perfect. So we're welcome back, and I now have all the values filled in. So if you need to, just pause the video, all right, and write them down. But you can see I put them all to the thousandths decimal place. And once again, you are finding ordered pairs here. So like, for example, this last one, this is at the x coordinate of 14 and the y coordinate of 17.916, right? So that would be the same for each one of these. I have found, well, essentially it's this. Each one of these are ordered pairs, okay? So we've plotted up till 3. Let's just keep going. So at 4, we are at 7.2, so right about here. And again, this is a graph. It's just an estimate. You don't have to be super exact, all right? Just kind of getting a general trend. So 5, you were at 7.8, like 9, so kind of like right below it, right below 8, like that. 6, it is at 8.64, so 6, 8.64, so halfway between 8 and 9 pretty much. 7 is 9.5 almost, so halfway right there. And then 8, you're at 10.4 roughly. 8 is 10.4, it's like right there. 9 is 11.35. Okay, and I'm gonna run out of room. 10 is 12.44. 12.44. 11 is 13.6. 11 is 13.6. 12 is 14.9. So it's pretty much at 15. And then 13 is at 16.3, sorry. So about halfway almost. And then 14, the last one is 17.9. So we're right up here. So you can see, you have this kind of nice curve like this. And that looks like an exponential curve, right? And that's because it is. It's an exponential function. So We'll go through the homework in class, all right? We'll just get practice doing these application type problems on increasing exponential functions or exponential growth problems. Bye for now.